Hello and welcome to Ampasimon. Today I'll share a presentation that was given at the Asia-Oceania Regional Council of Cigre Study Committee meeting for B2. The topic is on dynamic line rating application examples from Europe and North America. Let's start with a basic overview. Dynamic line rating concerns the current carrying capacity of overhead transmission or distribution lines. First, you need some kind of power line monitoring system, like a sensor. This monitoring system will give you visibility in real time of the asset condition, so the physical status of the overhead power line. The measured parameters then allow you to estimate the actual capacity of the line based on real-time ambient conditions. This means you are likely to obtain extra capacity above the traditional way of estimating line capacity and also ensure a safer use of the line so that you don't inadvertently overload it. Monitoring systems for dynamic line rating, there are predominantly three varieties. First is the line-mounted sensor, like Ampasimon provides. It measures directly the physical status of the power line, like sag, temperature, wind speed, and current. Tower-mounted sensors, or non-contact sensors, the second. Basically, devices monitoring local weather conditions or visual sensors, like cameras or LiDAR, that observe the power line. And third, there is the approach to have no monitoring at all, relying on computer-based modeling of weather. As you can imagine, the most accurate way to observe the power line is the direct method. Without local observations, there's no way to validate the accuracy of a model, and even then, you have to downscale it to account for uncertainty. With the tower-mounted system, the accuracy improves compared to the computer models, but you still have local differences in weather conditions, especially wind speeds, between the tower location and the power line. This is reported by several Cigre papers already. The discrepancy is greater if you have complex terrain or obstacles like trees and buildings in the area, or you have very long spans. And this is why, if the asset is critical and safety is important, it's best to use direct measurement systems. What the sensors and the monitoring system do is collect parameters that affect the cooling of the conductor. The conductor is heated when there's current flowing through the line, but it's also affected by the surrounding environment, from air temperature, solar radiation, and wind cooling effect. Cigre and IEEE recommend the heat balance equation for the conductor to calculate static or dynamic ratings. Static ratings is a fixed limit based on worst-case ambient heating conditions, while dynamic rating is a limit which reflects the actual ambient cooling based on field measurements. The ratings tells you the maximum amount of current that can be passed through the line until the safety limit is reached. The safety limits are defined by the maximum sag, typically by regulation to do with clearance safety to ground, and the maximum conductor temperature, which is a metallic material property of the cable. Here, a key point to keep in mind is that sag is the best parameter to measure. Why? Because it is a fixed reference point. The clearance can change over time, especially if there's trees or buildings under the line, and it indicates the holistic condition of the conductor cooling effect, which is necessary for calculating the dynamic line rating. I mentioned that dynamic line rating is a limit which reflects the actual ambient cooling based on field measurements. Here, you also have a variety of interpretations. As opposed to the first one, which is the classic static rating, a single fixed value all the time, you may have other types which have ratings that vary over time. Seasonal ratings apply fixed ratings per season based on the worst-case ambient temperature per season. Ambient adjusted ratings consider real-time ambient temperature. This is often used in the USA. But true dynamic line rating considers also wind cooling effect by measuring and forecasting wind speed. This form of dynamic line rating is most interesting to access latent capacity from the grid because very small winds, like below 4 meters per second, already give more than 50% extra capacity, while a 2 degrees Celsius cooler ambient temperature gives only 2%. This means that especially in hot climates, the true dynamic line rating is what should be used to assess when extra capacity is safe to use. So the key aspects for a good quality dynamic line rating system that maximizes extra capacity without compromising safety risks are that you need to measure with sensors the conductor sag, the effective perpendicular wind speed, the load current, and the ambient temperature. This will give you the most accurate real-time observability of safety limit infringement risk, the maximum sag or the clearance infringement, and the conductor temperature. To ensure safe operation of the grid, the real-time line ratings can be observed through platforms like Cigre. However, if there is only real-time information, you can only trigger a reaction in case of an overload. The smarter way would be to anticipate and prevent it, so that you don't trigger a knee-jerk reaction in operating the grid. This is why it's a very important feature indicative of a good quality dynamic line rating system that it has highly reliable forecasting capability. A testament to this is the number of utilities around the world opting to use line-mounted sensor dynamic line rating. Probably you can see from this list that they are predominantly European and North American, but we are starting to see adoption also in South America and Asia as well. Today, I'm here to share with you some results from observations in Europe and North America. So here we see observations from 6 lines, 3 from Europe and 3 from Americas. They all show at least 1 year of data, some of them more than 3 years. The red curves show the line current, blue the ambient adjusted rating, considering cooling from ambient temperature only. And the green shows the dynamic line rating considering cooling also from the wind. The static rating used by the customer is shown as well. In most cases, it's just a flat line, but the bottom 2 of the European systems show that it varies per season. Usually, the static line rating is set to a value that allows 2% of the risk of the ambient adjusted rating. That means that the blue curve may go below the static rating 2% of the time. Typically, this would mean values like 40 degrees in summer and 20 degrees Celsius in winter. There's a chance that such temperatures would be exceeded, but not very often. The top left system shows this classical setting of the static line rating. Flat the whole year, with the blue curve dropping below very few times. On the contrary, the top right system and the left middle system have static line ratings that are very aggressive. You see that the blue curve falls below much more than 2% of the time. In fact, even the dynamic line rating considering wind cooling falls below the static line rating sometimes. The numbers next to the graphs show the number of years of data displayed. You can see that the dynamic line rating is generally affected by seasonal weather characteristics, meaning there's more capacity due to cooler conditions in winter compared to summer. The difference is starker in some regions than others. The exception is the bottom right system, which shows no strong seasonal patterns throughout the 3 years of observations. This is a system in the tropics. The seasons can also affect the line loading, like the top right system, where there are high peaks in summer, and the middle right, where there are high peaks in winter. Perhaps you would think that dynamic line rating is useful only in areas where winter load peaks coincide with cooler conditions, releasing the capacity. But you see that customers find dynamic line rating useful also in cases where the high load situations lead to a tight operational situation to make visible and therefore control the risk. Another interesting observation is that in some systems, the wind cooling effect has a huge impact on releasing extra capacity. The top left and bottom right graphs show best this effect. The blue line considers only ambient air cooling without any wind cooling, while the green curve shows the capacity by considering wind cooling. What is interesting here is that the top left graph is in a relatively cool European location, while the bottom right is in a tropical climate. This goes to show that the maximum capacity extracted by wind is really useful in cases where the line loading is high, leaving little margin between the line loading and the static line rating, and also where the ambient temperatures are generally high and stable, so the ambient adjusted rating doesn't release a lot of extra capacity. One last thing to note is that in all cases, the load does not exceed the green line. To ensure an N-1 safe operation, typically for a radial line, you don't want to exceed 50% of the line rating, and for a meshed grid, rule of thumb is that you don't want to exceed around 70 to 80% of the line rating. The top left and bottom right in particular, you can see they adhere to this classical operational approach. However, some cases, like the bottom left, the load exceeds the static line rating, but it does not and should not exceed the green line, which is the true capacity of the line. Now we see the same systems, but in the ratings and line loadings in the form of duration curves. Here you can see that the characteristics of the green line in relation to the blue line is the same for all systems. wind cooling releases overall extra capacity compared to just the ambient cooling. From the observations here, as well as the 70 other systems we have in operation around the world, we see that typically at least 20% of extra capacity is available most of the time. With full proper dynamic line rating systems, this is made available just by retrofitting a few sensors on a line and installing the monitoring software. It can be and has been put into place from the stage of sending a request for installation to a fully functioning system in a few months. Also, the steps of fully integrating the data into your SCADA can be done in under a year. The screenshot here has been shown many times. It's from the control room in the National Grid Control Center at Belgium. The data highlighted in the yellow box there under limit 1 hour capped is the data streamed from the sensor-based dynamic line rating system. It's updated with a new value every hour automatically, and it's fully integrated into this SCADA screen used by operators on a day-to-day basis. The actual line rating changes in real time according to weather conditions, which is not stable throughout an hour. And this is why, for the application here in Belgium, the customer requested to display in the SCADA the 1 hour ahead forecast rating, which is the minimum value of the dynamic line rating based on weather forecast over the next hour. I try to explain about the forecast dynamic line rating with this graph from a line in Belgium. The graph shows the static line rating at 100% in red and the line current in brown. The actual full dynamic line rating which the system saw in real time is the solid green line. However, the value we saw in the SCADA in the previous screen is the 1 hour forecast value, which is the blue solid line. While the green line changes every 5 minutes, the blue line stays static for an hour. On top of this, in Belgium, they capped the maximum usable dynamic line rating at 130% of the static line rating. This is because of the thermal limit of other equipment in substation bays, which cannot tolerate higher loadings. Even if the conductor could carry more current, other pieces of equipment may not be able to cope with that. You can see that in the line current exceeded the traditional static line rating, but never exceeded the forecast or the real-time line capacity ratings. They were able to permit this high line current only because they had the visibility of the true line capacity, both in forecast value and in real-time value. The wind cooling effect on the line gives a significant boost to the available capacity above the static line rating and also above the ambient adjusted rating. The example I show here is from a 380 kV line in Germany. The horizontal straight line is the static line rating, the dark red curve is the line current. The green shaded area behind the line current curve is the sum of the wind and the PV infeed at that time in gigawatt hour per hour based on 15 minute data. You can see that the high line currents are driven by PV peaks and high wind infeeds. Now we shift our attention to the dynamic rating considering wind cooling, the green curve, and the ambient adjusted rating, which does not consider wind cooling, but only air temperature cooling, which is the purple curve. It's intuitive that if there are high winds causing high wind infeed, and this is causing the high line loading, at the same time, the same winds should cool the power lines and create extra capacity. And essentially that's what you see here, but a little bit more. First, at the moments when high line loading is caused by high winds, the dynamic line rating is also high, naturally. Secondly, what you see is when the high line loading is caused by PV, this is typically in the middle of the day, so the hottest part of the day. If wind cooling is not considered, the ambient adjusted rating, the purple curve, gives some capacity, but actually it's at its lowest point throughout the day. Whereas the green curve, which considers the wind cooling in addition, gives ample headroom. So it's effective for wind integration, but also for PV. The correlation between wind infeed and high line loading is observed not only in Germany but also in France. This result here is from 3 years of accumulated data from a line in northern France. The statistical distribution of the line current resulting from different levels of wind infeed is shown. You can see that high line loading above 70% results when wind infeed is high, at least 80% of its installed capacity. Now a similar graph, but showing the correlation between dynamic line rating and wind infeed. From the previous graph, we know that critically high line currents occur when the wind infeed is above 80% of its installed capacity. These are the moments where you want to have extra capacity from dynamic line rating at those instances when the line loading is high. So we can see from this graph that on average, there is about 150 to 20% line capacity or 15 to 20% extra capacity above the static line rating in these moments when the wind infeed is high. Also, you can see that there is a positive correlation. So there is a tendency for extra capacity to be available when the wind infeeds are high. Deriving from this kind of correlation, in France, it was decided that dynamic line rating will be used as a key technology in combination with infeed curtailment to accelerate the acceptable connection of new wind farms. They reported in an IEEE journal that the hosting capacity can be increased up to 50% without the need for reinforcement by using dynamic line rating to trigger automatic curtailment. The last project results I want to share with you is from the USA. Here we see over 1 year of data from a line. Strong seasonal and diurnal demand patterns due to air conditioning is visible. Also, the nominal static line rating is quite high. Normally, you would expect the ambient adjusted rating to be below the static line rating 2% of the time, but in this case, it's 25% of the time. For this line, the N-1 limit, or the operational line limit, is around 70% of the static line rating. At this location, the ambient temperatures can be pretty high. This graph shows the monthly temperature ranges in the last years, 2019 and 2020. In the summer, the temperatures reached over 45 degrees Celsius, while the static line rating is set based on the worst case assumption being 43 degrees Celsius. Zooming in on those days with extremely high temperatures exceeding 45 degrees Celsius, we see that the line loading is also very high because everyone is using air conditioning. The line current exceeds 70% of the static line rating, which by a traditional operation approach would be considered an N-1 violation. Because they have their line equipped with line-mounted sensors, they can monitor in real time the safety. At the same point in time as those high load periods, you can see in this graph the corresponding sag in the dark red and conductor temperature in the purple. The system gives you visibility to monitor how close the line is operating to the real limits, so we know that they are not exceeding the safety limits here. Again, for the same time period, we see in this chart the corresponding ambient temperatures in orange and the wind speeds in blue. What you can see here is that during the high temperature peaks, the wind speeds also tend to be high, so it's counterbalancing the heating from the ambient temperature with wind cooling effect. The result of capturing these wind speeds in the ratings are shown in this graph. The green curve is the N-1 limit based on the real-time dynamic line rating. This means the extra capacity gained by cooling effect is the green shaded area. This means that if you consider the N-1 limits based on static line rating, the line would be considered overloaded at these peak times. But if you consider the wind cooling effect, the N-1 limit is increased and the line current can be safely carried without risking an overload situation. Just one last point to make here, the light blue curve. This shows the ambient adjusted rating, so the rating without the wind cooling effect. Ambient adjusted rating is often used in the United States because it's easy to measure the ambient temperature. But what you see from this system is that in areas where high temperatures coincide with high load currents, ambient adjusted ratings doesn't help. Only if you consider wind cooling effect do you access the true benefit of dynamic line rating. Now to the summary and concluding remarks. First, line-mounted sensor-based dynamic line rating is most accurate, but various types are used based on the utility's attitude towards risk management. Second, utilities in varying climates and terrains in over 15 countries use line-mounted sensor-based dynamic line rating. based on observations from more than 10 years and over 70 systems, conclude that at least 20% extra capacity is available 90% of the time. A good quality dynamic line rating system is characterized by forecast dynamic line rating considering wind cooling effect, that it provides a visibility of risk, the data is integrated into the control room, it measures critical parameters for accuracy of gain and risk. Clearly, dynamic line rating application for wind integration is effective, but it makes also sense to leverage wind cooling where and when little ambient cooling and where operation is tight. Finally, benefits of dynamic line rating are accessed by using them as the real-time limit or the real limit for line operation instead of the static line rating. And for this, forecast and SCADA integration is essential. Thank you very much for your attention. Please feel free to send me any questions or write in the comments below.